Hello.
Yes,
Good morning.
Yes.
Sridhar, should I start now?
Yes, sir. Sorry. Please go ahead.
Okay. Hello again. Good morning. This is Ratneswar Jha presenting this webinar from the campus of Clarkson University. Clarkson is a small, independent, which means private school. It's a technological school. That means it's very much focused on engineering and science. Clarkson is situated in a small community which is called Potsdam. It's in the upstate area of the state of New York. It's far away from New York City. This is a very small place actually, but it's very beautiful. As you can see here on the map of Clarkson, lots of trees, shows the fall color in this season. And I'm here in one of the buildings at the back, which is actually the engineering building. I'll give you just a little bit of my background, just one slide. I graduated from IIT Kharagpur in '81 with a degree in aeronautical engineering. Then I joined Georgia Tech and completed my Master of Science in '82. And then I worked in India, actually at HAL Bangalore from '83 to '95, designing the light combat aircraft. You can see here light combat aircraft model in the wind tunnel, and on the right here, the same model in the wind tunnel. I'm sort of checking something, one of the external stores. This is about 20 years back. After working there for 12 years, I came back to US, joined Arizona State University, the Department of Mechanical and Aerospace Engineering, and got a Ph.D. in Mechanical Engineering in 1999. And then I joined Clarkson University as a faculty member, and I've been here for the past 12 years. My research areas are given here. Most of them fall in what we call smart structures, and that's what you are going to hear about quite a bit today. Some of the specific areas are adaptive vibration control and structural health monitoring. In structural health monitoring, one can do a vibration-based health monitoring or a wave propagation-based health monitoring. And I'll talk mostly about the wave propagation-based health monitoring, though we have done both. I also work on active flow control. I'll talk about it very, very briefly. Quite a bit of my work relates to the composite structures. So I do mechanics or modeling of composite structures. And actually some of the wave propagation work, or actually all of the wave propagation work that I'll show you, are for composite structures. I also work on micro air vehicles and prognosis, or the prediction of remaining useful life of a structure. So coming to smart structures, you may be wondering what smart structures are. Smart structures are actually the regular structure that we have, which generally just take load. To that, if we can add some other function, and that function may be reduce the vibrations or minimize the vibrations or minimize noise, or the structure can change its shape and size. Say an airplane wing can change its shape and size during flight. Those are some of the applications of smart structures. These are really innovative structures. The structures can perform new functions in addition to the primary function of carrying load. The idea is to get significant benefits at the system level. System level meaning the overall working of the structure. Of course, whenever we do any of these things, add the smart component to a structure, it makes the structure much more complex. So the system level benefit has to be looked at with respect to the complexity that we add. The diagram which you see here on the right-hand side bottom, that sort of pictorially shows the basic idea behind smart structures. Smart structures has people or takes disciplines that are from mechanical, aerospace, civil engineering, electrical engineering, as well as material science and engineering. From material science and engineering, we get these active materials or the smart materials, which are the key ingredient or key part of the smart structure, and I'll talk about that on the next slide. From mechanical, aerospace, or civil engineering, we essentially look at the structural mechanics or system design or the overall system, what it will do, how it will function. From the traditional electrical engineering discipline, we take the ideas from control system design for active vibration control, active flow control, and such things. A lot of signal processing is involved in smart structures, especially in structural health monitoring. So actually my work centers around these two here: structural mechanics, system design, control system, and signal processing. As far as active materials are concerned, I just use active materials. I myself don't do any research in designing or fabricating active materials. Now these active materials are the so-called smart materials. They fall in several categories, but essentially what they do is to transform one form of energy to another form of energy. For instance, let's take the piezoelectric materials. Piezoelectric materials have the property that if you give an electrical charge, the material would have a mechanical strain, or if you give a mechanical strain, it will generate an electrical charge. Due to this reason, piezoelectric materials can be used both as actuator, where we give an electrical charge and it causes a strain, which may cause a vibration, which may cause a wave actuation or a wave propagation to start, or it can be used as a sensor to sense vibration signals or wave propagation signals and such things. And I'll talk a little bit more about this. All of my work, actually, we use piezoelectric material. In that, a particular one we use is called PZT, which is lead zirconate titanate. There are other smart materials which are equally important, and other people use them for their applications, and one of them is called shape memory alloy. Now shape memory alloys have actually thermal energy and mechanical strain going back and forth. So if you apply a thermal energy, it will have mechanical strain, and the strain can be much larger than the strain in the piezoelectric materials. However, shape memory alloys work at significantly lower frequencies, say 1 Hertz or 5 Hertz, whereas piezoelectric materials can work at very high frequencies, even going up to megahertz. We use them at low frequencies, that is up to say 100 Hertz, as well as high frequencies going up to 100 kilohertz or 100,000 Hertz. Another very important class of smart material is magnetorheological fluid. These actually are being used for certain cars in their shock absorbers to increase the damping through magnetic field that is applied around the fluid. So these shape memory alloys, you can find a lot of material on those if you search on the web. Especially there's a company called Lord Corporation. They do a lot of work in that. They do a lot of work in magnetorheological fluid. For shape memory alloys, there's a consortium, Shape Memory Alloy Consortium. They have a lot of publications. I'm not going to talk about them anymore because in my research, we use piezoelectric materials. So let's see how piezoelectric materials are being used. Here is a photograph from one of the experimental setups in my lab. What we see here is an aluminum plate, and that is fixed on this side here. And this fixture that you see here has the capability to go up and down. In other words, we can vibrate this aluminum plate, and there is a shaker below it, so we can vibrate at any frequency, any amplitude that we want. Now, these brown patches which you see, these are the two piezoelectric actuators which are attached to the aluminum plate. To these piezoelectric actuators, when we apply an electrical voltage, and we generally have been applying to these actuators plus minus 200 volts or somewhat less than that, they will have a mechanical strain. And these actuators are only on one side of the plate. The other side of the plate, there's no such strain, so plate actually bends. And as you apply positive voltage or negative voltage, the plate would bend up or down. If you apply this voltage at a certain frequency, let's say 100 hertz, 100 cycles per second, you'll have a vibration in the plate. Or we can use the strain in the plate or the vibration that can be caused by these actuators to counteract the vibration which is in the plate from some other source. So let's imagine, say, an airplane wing. Of course, that's a very large one, but imagine a large number of actuators on airplane wing. When there's a vibration, we give some voltage to the actuators and it reduces the vibrations. It's exactly the same idea here. Of course, we are applying here to much simpler structures, because the focus of my research that I'm going to share with you shortly is on the design of the control laws to calculate the voltage, the appropriate voltage that should go into the PGT actuators. These control laws play a very crucial role. We have used some new and innovative techniques to design those control laws, which have been published in several papers, which I'll list at the end. So this vibration suppression is one of the areas where we have used PGT actuators. Another area where we are using currently PGT actuators is for wave actuation and sensing. And this is related to the health monitoring of a structure, or finding whether a structure is damaged or not. What we see here on the left-hand side is a roughly 16-inch by 12-inch composite plate. This composite plate has been made in my lab out of 8 layers of unidirectional carbon fiber prepreg composites, which is laid, vacuum bagged, and put in an oven to bake sort of for a couple of hours, and then the plate is ready. To this plate, we have attached here what I'm showing you on the right-hand side, 6 PGT actuators. Now these actuators, which can also be used as sensors, are much, much smaller than what I showed you earlier. These are actually less than 1 centimeter in diameter. But these are good enough for us to be able to generate waves, a particular kind of waves called Lamb waves in this plate, and sense them. We have been using voltage of plus minus 100 volts generally. Let's say one of these actuators has a voltage input plus minus 100 volts at a certain frequency, let's say 20,000 hertz or 20 kilohertz. This will send out a wave in the plate. That wave motion will cause certain strain in these other PGT patches that we have, and that strain would cause a voltage or a charge which would be sensed. So in other words, the wave motion can be sensed by any one of these PGT actuators or sensors. Now, if the plate is healthy, we'll have certain kind of wave motion sensed by all these sensors. If the plate is damaged, let's say it has a delamination, that means there's a gap between, say, 4th and 5th ply. In that case, the wave motion would be different, and therefore the sensed signal would be different. And by doing the signal processing, we can tell whether there is a damage in the plate, where is the damage, extent of the damage, and such things. There's a lot of structural mechanics also involved in this. If you want to do complete damage detection, I'll talk a little bit about that, but just to give you an idea here, the propagating wave interacts with damages, and by doing a lot of signal processing using Fourier-based analysis methods, wavelet-based analysis methods, other analysis methods, something called Hilbert-Wang transform, and many others, we can detect damages. So this will be the second part of my talk, which I'll present to you in a few minutes. I just want to show you one more thing, and this is related to active flow control. Now, since I'm basically aerospace engineer, I talk about airplane wings quite a bit. Airplane wings, as you may know, beyond a certain angle of attack, there is a separation of flow on the top surface of the airplane wing. That flow separation causes reduced lift, increased drag, and other disadvantageous phenomena like maybe buffet and such things. So we always want to reduce that flow separation. At the same time, we want to fly to high angles of attack. So the idea here is, can we do something to actively reduce flow separation? And there's a lot of research going on in this area. This is called active separation control or active flow control. Of course, to do the active control, we need some kind of actuators. So there is a class of actuators known as synthetic jet actuators. Here is a synthetic jet actuator. It's sort of made out of a semi-transparent material so that you can see. Inside this synthetic jet actuator, the round thing that you see here essentially is what is shown here in this figure on the left. Is a piezoelectric actuator which has been attached to a brass plate, sort of yellow color. And this red dot that you see here in the center, that red is coming from a laser beam being focused at the center of the piezoelectric material. Now to this piezoelectric material here, this circular patch of about 3 centimeter, when we give a voltage at a certain frequency, this would have vibration. And on the right hand side, you see the vibration deflection shape that has been captured using a laser vibrometer for this piezoelectric disc that we have on the left hand side. This vibration shape actually is, if you look at in 3D, it's a dome shaped. That means the maximum amplitude in the center and zero amplitude at the periphery, where the plate actually is constrained by putting a ring and putting some screws around that. Now, when this vibration takes place inside this actuator, of course the plate is vibrating up and down, so it's forcing air through a small orifice or a number of orifices which is on the right hand side of this actuator. The top surface actually is like an aerofoil surface, so that it will appear this is just like a wing surface, but small jets will come out through the orifices here, and they will energize the flow and thereby reduce flow separation. Of course, the control law again plays a very crucial role here, and my involvement, this is a very large project involving several faculty members here at Clarkson. My involvement is essentially with the control law. However, I'm not going to talk more about this. I'm going to talk about active vibration control and structural health monitoring. To do this work, I have a lab which is called Composite and Smart Structures Lab. Here I'm showing you a couple of photographs from the lab. As I mentioned, we have a scanning laser vibrometer. This is a very sophisticated piece of equipment which costs about $200,000. With this, we can either sense vibrations on a plate. We can also sense wave propagation on a plate remotely without putting any sensors on the plate, and that's what we are trying to do here. We have used this vibrometer also to sense vibrations from a large structure, which is the kind of bridge structure here. Some of my work relates to the health monitoring of bridges. We have used this laser vibrometer to sense vibrations of a very thin piece of wing which may be used for a micro air vehicle. And what you are seeing here on the left hand side is a finite element prediction of the vibration shapes, and on the right hand side is the scanning laser vibrometer measurement of the vibration shapes. So this is just to give you an idea about the Composite and Smart Structures lab that I have here. Now coming to the active vibration suppression, the first topic which I'll go into detail. But before I go there, I would like to invite any questions that you may have. Please type in your questions, and Sridhar will be able to read those questions to me, and I'll be glad to answer before moving forward. Okay, I didn't hear any questions, so maybe there are no questions at this time, and therefore I'll move ahead and talk about the active vibration suppression. This is extremely important to improve the performance of a structure and also to improve its fatigue life. Now, the smart structures, which are also known as adaptive structures, sometimes intelligent structures, have been extensively used for reducing vibrations. And much of that actually has to do with space structures, which are very light, and even a small amount of vibration actually can significantly reduce their functionality or compromise the missions for which they are there. Now, to perform vibration suppression, we need generally a high fidelity model of a structure. But many of the structures are very complex, and getting a high fidelity linear model is not very easy. Therefore, we went with designing a neural network based controller which does not need that high fidelity model of the structure. We have used neural network based controller, which is known as neural adaptive predictive control, and we have also compared its functioning or its performance with respect to non-neural network based controller, and I'll show you some of those as we go along. Now, this adaptive predictive control actually is based on the idea of model predictive control, which is pretty well established. You have a model of the plant, which may be just a plate which is vibrating, or maybe airplane wing or a spacecraft. You looked through the model how the output or what will be the vibration of this structure in future, and based on that prediction you calculate what should be the input signal. There are quite a few advantages of such a scheme. It's intuitive, it's easy to tune, it's applicable for open loop unstable systems as well, but there are some drawbacks. You need a good plant model, and computation is required at each sampling time for adaptive control. This is a sketch of our adaptive predictive control system architecture. You'd have the actual structure here, or the plant as we call. To that there's some kind of disturbance, which may be, say, turbulence in the air for an airplane wing. To that structure we are giving a certain input voltage to the actuators on the structure, and we get some output which is essentially vibration in this case. We take that output and we have a plant of the plant model of the plant system model, which is a neural network based model for the actual structure that we have, and to that we apply the same input as we apply to a real structure, which gives, then the plant gives some output, or the model gives some output. We compare that output with the actual output. There's a difference there, so that means there's an error. We use that error to retrain the plant or train the plant adaptively, and then the plant predicts what is going to be the next sequence of the control. Once we go through this a few times, we optimize the control signal, and that optimized control signal is given to the plant for vibration control. So this whole thing actually runs sort of iteratively. This is the neural network based controller or model of the plant that we have designed. Is a relatively simple one. There's just one hidden layer which has the so-called sigmoid neuron, and there's one output layer which has a linear neuron, because we are looking for a single value of vibration at the tip of the plate. This is some detail of the online learning algorithm. There's a lot of math involved in this, which are given in my papers. I'm not going to go into details of these, but you are certainly welcome to look at the papers, and if you have any question, you can email them to me. I'll be glad to answer those. This is giving how the control law is designed for both the neural network based controller as well as the conventional adaptive controller. Here is a sketch of the experimental setup. We have the actual structure with the piezoelectric actuators that I showed you earlier. A shaker actually shakes the plate, as you see the shaker here in the left figure, and we shake it actually quite well so that the plate actually has nonlinear vibrations. The vibrational amplitudes are relatively large. We have an accelerometer, as you see here on the left-hand side, that is to sense the vibration. The signal from the accelerometer goes to a signal conditioner through a filter, and A2D board goes into the computer, which has the control law that is running. It gives the signal to the D2A board, which goes to the piezo powered amplifier, and which sends signal finally to the piezo actuators. Now here I'm showing you the performance of the controller that we designed. You look at the left-hand side, the blue line shows the uncontrolled plant or uncontrolled plate vibrations. This is in frequency domain, and this is at the first natural frequency, or very close to that, about 6.5 Hertz. The black line shows that there's a significant reduction in the vibration due to the conventional adaptive predictive controller. But the neural network-based adaptive predictive controller that we have designed and implemented shows even higher vibration suppression. Very similar thing on the right-hand side, but for the second mode, or slightly higher frequency, around 40 Hertz. This shows the same information, but in the time domain. We are again looking at the tip acceleration, uncontrolled in blue, and with neural adaptive predictive controller in red on the top, and same thing, uncontrolled in blue, but the conventional adaptive predictive controller in red at the bottom. And you can see we're able to reduce vibration by 85% or 90% or more. If you change the frequency of the disturbance from first mode to second mode, you can see how the controller actually adapts and still is able to reduce the vibration very significantly, more than 80%. This case here is a very interesting case which we did. We started the plant without any control, and then we dropped a small mass on the plate, and we gave the input signal to start with, the vibration signal, such that it would go into resonance once we drop the mass. So that is the no control case. Now when you come to the control case, we again do the same experiment. We start by the plate without the mass, and after some time we drop the mass. So now the controller knows that there's a large vibration, and the controller learns online in real time and suppresses the vibration. So as you can see, from no control case to the control case, there's a very large reduction in vibrations. So based on what I have shown you briefly, I would like to conclude that we have designed neural adaptive predictive controller, which has given us large reduction in vibrations. The controller is suitable for nonlinear and time-varying structures. The neural network-based controller is better than the conventional controller. There's a nonlinear optimization involved, of course, so it can be computationally expensive, but we have been able to show that this can work in real time. If you are interested in further details of the work that we have done in this area, I have listed here 6 of my journal papers, which were published some time back, but they are, still very, very relevant, and they give all the mathematical details which you can go into. Now that is all I'm going to talk about the neural network-based controller. I'll switch now to structural health monitoring, but I'd like to ask you if you have any questions. I would be glad to try to answer those questions. Sridhar, are there any questions at this time?
Yes, sir. 1 minute.
Okay.
The one question says, any logistic model for adaptive control, since data analysis will be small in number in case of log?
Can you read it again, please?
Any logistic model for adaptive control, since data analysis will be small in number in case of log?
Okay, I'm not very sure what the question refers to, but based on the small part that I understand, let me say it let me try to answer this. Now, the data that we're getting is as per the accelerometer signal. So the accelerometer signal shows what is the level of vibration in the plate. That through the signal conditioner and filter finally goes into the computer. For real-time control, the control signal which is sent to the piezo actuator has to be really, really quick. So for real-time control, actually running it with a computer in the loop is not the best option. A better option is actually to use what is known as a D-space based board or some other hardware based control implementation. But we were running it at 100 Hertz or so, and this was maybe about 7-8 years back, and the PCs were not that powerful. Still we were able to control everything up to 100 Hertz using a very ordinary PC. So of course there are algorithms related to this, and some of those are mentioned in the papers that I have. Sridhar, any other questions?
No, sir, not yet. We will take them later, sir, if you want.
Okay, so I'll go ahead and talk about the other topic. So the other topic is related to the health monitoring of structures. Now, as all of us know, the engineered systems, they have failure, like aircraft fuselage being blown, bridge being broken, and such things. Currently, all these engineering systems, they are maintained based on a certain schedule. After a certain number of hours of flight, after certain, say, every bridge in US has to be inspected at least once every 2 years and such things. Now, due to that schedule-based maintenance, sometimes failures occur before the maintenance is performed. Many times maintenance is performed or inspection is performed even though the system or the structure is healthy. So there is a move to a newer system of maintenance which is known as condition-based maintenance. Now, in the condition-based maintenance, we would know the condition of a structure by attaching certain sensors and actuators to the structure and doing the signal processing on the signal that we collect. And based on that condition of the structure, we will perform maintenance or we will not perform maintenance. We will wait till the structure has any problem. Now, this is a big topic by itself, and this is known as structural health monitoring, or SHM. Now, right now the maintenance that is done or the inspection that is done is based on what is known as non-destructive evaluation or non-destructive inspection. The idea is, in SHM, can we integrate all the functionality of NDE or non-destructive inspection with the structure? But of course, non-destructive inspection or evaluation equipment are very, very large. So of course, that cannot be integrated with the structure. So we have to go for some relatively or very, very small kind of actuator sensors. And that's why what I mentioned to you earlier, we use piezoelectric actuators which are less than 1 centimeter in diameter, and they are less than 0.5 millimeter in thickness. This would have tremendous benefits. Of course, this is not an easy task, because for structural health monitoring or damage detection, we want to know not just the presence of damage, we also want to know where the damage is located, at least approximate damage location. What is the type of damage? How severe is the damage? What is the extent of damage? And much more importantly, and much more difficult to do, is to predict the remaining useful life. So these are sequence of five tasks. They are roughly divided into the first 4, which fall under structural health monitoring, and the last one is generally referred to as prognosis. So there are 4 tasks related to diagnostics or diagnosis, and 1 task related to prognosis. All of them many times are lumped together, and they are called structural health management. My work, what I'm going to show you today, relates to just the diagnostic part. I also work in the prognostic part, but that is a separate topic by itself, which I will not be talking about today. Now, in the diagnostic part, what I'm going to focus on is health monitoring using guided wave. And these are elastic waves that propagate in structures. And guided wave means, let's say we take a thin plate, these waves propagate along the length and width of the plate. They are guided by the upper and the lower surface, or they are bounded by the upper and lower surface of the plate. So they propagate through the thickness of the plate along the length and width of the plate. In that, we have done quite a bit of work actually. We are working with a professor at IISc Bangalore, Professor Gopal Krishnan, on this wavelet-based spectral finite element, and actually we have a joint funding by US Air Force, or Air Force Office of Scientific Research, to work jointly. We have also worked on a newer method for finding the damage in structures, which again uses information from the spectral finite element. This method is known as damage force indicator method. We have just modeled, using the spectral finite element or wavelet-based spectral finite element, a transverse crack in a composite plate. This is just numerical modeling or a mechanics-based modeling. We have done experiments to find damage in composite plate by a method known as a modified time reversal. And I have publications on all of these, which I'll show as I go along. I'm going to touch upon these very briefly. So the guided wave essentially refers to a case where you have a wave which is passing through the plate length and width. Generally, the kind of waves that we generate and most people use for structural health monitoring are known as Lamb waves. And these Lamb waves can propagate through the thickness as well. So even if we have some kind of damage in the thickness of a plate, we can detect that damage. This is not very new. People have been working with this for a while. So why are we trying to sort of emphasize this? We're trying to emphasize this because the work that has been done so far generally refers to the structural health monitoring using what is known as the baseline data. Baseline data meaning you have a plate which is healthy. In that plate you send some kind of wave from one end, let's say, and you sense it at the other end. So you store that data. Now the same plate or similar plate which is in operation, and that plate has some kind of crack or some kind of other damage, and you get data for that plate. And now you compare the two data. Now as you compare the two data, you'd see some difference between the two, and from that you can tell there's a damage. But there is a big problem in this approach. The problem is it's very difficult to generate healthy data for all kinds of structures under all kinds of operations that they will have and the environmental conditions that they will experience. So relying on the baseline data is not very good for practical structural health monitoring. So we have been trying to actually move away from baseline data-based health monitoring. And that is where this spectral finite element that I mentioned to you earlier actually is very useful. In addition to that, spectral finite element is also useful in a sense that it can reduce the computational expense by at least an order of magnitude. This computational expense is very important for structural health monitoring because let's realize that structural health monitoring is essentially an inverse problem. Inverse problem meaning we have some signal from a structure, we want to find whether the structure is damaged or not. That's an inverse problem. A forward problem is we know we have a damage in the structure. If you give this kind of signal, what is the kind of output signal that we'll get? That is a forward problem. but SHM is an inverse problem. Having a mathematical model which is very efficient is extremely important, and that's where the wavelet-based spectral finite element is very helpful. Here are some more details for the spectral finite element, which I'm not going to go into in the interest of time. There's a paper here which is referred. You can look at that. That gives more details. Excuse me. I'm going to focus more on the experimental work that we have done here. This is on the top left, a composite plate, which has two versions. In the first version, the plate is healthy. In the second version, the plate is delaminated. There's a gap created between 4th and 5th ply of this 8-ply composite plate. Into this plate, we send a tone burst excitation at 20 kilohertz. This is the form of the excitation. Lasts for a very small fraction of time, but it generates a wave using this Ph.D. actuator here. So this composite plate, which is about 25 centimeter by maybe half of the size in the width, we have a single piezoelectric actuator. Excuse me. That piezoelectric actuator generates the wave, and we sense that wave using this laser vibrometer here. That's what is being shown here. Using that scheme, we have actually validated the results that we obtained from the numerical computation using the spectral finite element. And that's what we see here. In black is the numerical results using the wavelet-based spectral finite element. In red is the experimental result. On the left-hand side, we have for one sensor location. On the right-hand side, we have for another sensor location. Both of these are for the healthy plate. Looking at this excellent comparison, we can tell that the spectral finite element models that we have, they are valid. So we can use them for damage detection. Now, if we look at the experimental data alone, and let's look at the data plot here at the bottom, we have the healthy plate wave response, which is in black. When the plate is delaminated, we see the response in red. And this is at a sensor location S3, which is on the other side of delamination area. What we have here is an actuator shown the way I'm showing here, close to S7, and that sends some kind of signal at 20 kilohertz, the tone burst signal which I mentioned earlier. That comes through the plate length, interacts with the delamination, and has certain signal. Of course, it gets reflected as well, so you'll see some difference in signal between healthy and delaminated, even if we are on the same side of the delamination as the actuator. But on the other side, we generally see a larger difference, and that is what is being shown here. You can see there's a very distinct change in the frequency and the amplitude of the signal. So by finding the difference between the two, we could tell that there is a delamination. But of course, as I mentioned earlier, we don't want to rely on the healthy data. We can rely on the healthy model of the structure, but not data from the baseline healthy structure for all operational and environmental conditions. That is practically not feasible. So we try to do damage detection without using the healthy data, and one of the ways we have implemented that is known as a damage force indicator method. And what you see here, especially on the plot on the right-hand side top, is that we are able to detect damage at the correct location, which is shown by this normalized damage force indicator here. At other locations, that indicator is almost zero. There are much more details of this given in my paper, which is listed here at the bottom. If you are interested, you are most welcome to look at that paper. Another part of the work that we have done using the wavelet spectral finite element is to model a transverse crack. So there's a crack here again in a composite plate. In this case, we use two elements. Element 1 on the left-hand side of the crack, element 2 on the right-hand side of the crack. If the structure is continuous without any damage, we can model entire structure using a single element, which might need actually thousands of elements using the regular finite element, and that's what brings the computational efficiency in the spectral finite element. So for this cracked plate, actually, we have done the modeling, and you see some results here. And there is a web link. You can go and see here for the wave propagation. This will show wave propagation in this plate. As the wave propagates, it interacts with the crack. A part of the wave goes forward, a part of the wave gets reflected back. So essentially showing us, at least qualitatively, that our modeling is correct. In future, we'll use this model for damage detection in composite plate. Coming to the last topic in structural health monitoring, we have developed a method called a modified time reversal method. And what I'm showing you here is a completely experimental part. This we have published earlier in 2009 paper. This modified time reversal method, what it does is you actuate from, say, point A, you receive signal at point B. You take that signal and reverse it in time. Reverse it in time means the signal that you receive last, you send it out first, and signal that you received first, you send it out last. So you reverse the signal and send it out again from A, and again sends it at B. Now in that process, if the structure is healthy and behaves linearly, the two signals, when you compare, not in the amplitude but in the frequency and such things, they should compare and be almost the same. And therefore we can say that there is no damage. If there is a damage, the signals won't compare that way and the damage would be indicated. And that's what we have done here actually in this composite plate, which you see on the top left. Composite plate with 4 piezoelectric actuators. This plate is actually cantilevered, and only the wiring actually is hanging from this wood beam that you see here. This is an actuator. We have used 20 kilohertz 9.5 cycle tone burst. This is the plate, about 10 inches by 5 inches. We have damaged the plate first at A, and we just kept it same damage level at A. But at B, we incrementally damaged by dropping this steel ball from a certain height, say 4 feet in this case, at this point B 4 times, 8 times, and 12 times to cause different levels of damage. And we were actually able to show that with those damages, the damage index that we have defined actually increases monotonically, very, very consistently. We have used 2 different damage indices, and both of them compared to the baseline case, which is what we have normalized against, the both damage indices actually increase very consistently. Also, these damage indices increased only for the signal path from 1 to 2, which passes through the damage area. When we looked at signal paths, say 2 to 3, 1 to 3, and others, they did not show any increase, any significant increase in the damage index. So we know that the plate is damaged only along signal path 1 and 2. Increasing level of damage is shown clearly, and the plate is not damaged elsewhere. So through this, we're able to actually roughly locate damage and have some correlation with the extent of the damage. So to summarize the presentation that I've given you on the structural health monitoring, we have talked about wavelet-based spectral finite element, a damage force indicator method, which actually uses the stiffness matrix from the wavelet spectral finite element, and a modified time reversal. I've also worked with civil engineering structures, and what you see here is a large bridge structure, actually 4 meter by 1 meter, with several wireless sensors attached to the bridge structure. I'm not going to show any results for this. All these results actually are given in the paper here, given on the right hand side bottom. Finally, what we would like to do actually is an integrated diagnostics prognostics, so the complete structural health management of a structure, which would have diagnostic elements that I mentioned to you earlier, as well as the prognostics, that is predicting the remaining useful life. That is something which actually we are working on, and hopefully sometime in future we'll have that work done. I'd like to acknowledge my students and collaborators and also the agencies that have sponsored my research, which is Air Force Office of Scientific Research, National Science Foundation, and New York State Energy Research and Development Authority. With that, I'd like to thank you for listening to me. Here are my contact details. You can go to my webpage, people.clarkson.edu/RJHA. To look at copies of some of my papers, some of the presentations, complete list of my publications, and also the contact address, which is of course also given here. Thank you very much. I would like to try to answer any questions if you have.
Sir, one question is.
Are there any questions, sir?
Yes, sir. One question is, what is 2D FEM?
That refers to the two-dimensional finite element, which is the regular finite element, which people have been using for a long time. Is available in many software packages like ANSYS, Abacus, Nastran. That's what we mean when we say 2D FEM.
Yes, sir. The next one says, can you explain inverse problem?
Okay, so in general, engineering problems you can look at as two problems: forward problem and inverse problem. A forward problem is, let's say we know that there is a structure which has certain amount of damage. In that structure, if we send out a signal, if we actuate a signal, what would be on the other side of the damage? That is a forward problem. In structural health monitoring, actually, we have an inverse problem, meaning that we have the signal from a damaged structure or a possibly damaged structure. We need to find out whether the structure is healthy or damaged. So that class of problem is referred to as an inverse problem.
Okay, sir. The next question says, please explain what is tone burst excitation and how it is generated.
Okay, a tone burst excitation is, let me go to that slide here. Okay, what we see here on the upper right hand side is known as a tone burst excitation. This is essentially a sine wave which has been windowed using a Hanning window. So it has only a few number of cycles of sine waves. So this actually is a 3.5 cycle of sine waves. So this excitation is what we send to the PGT actuator as voltage. In the sense you send, say, this much voltage at this time, this much voltage at this time, this much voltage at this time. So you can discretize it, say have a 200 points, and those 200 points are sent out at those times. This is, look at the x-axis, which is in microseconds, to the PGT actuator. This is a way to generate a wave. This way of generating a wave is very useful because these Lamb waves are dispersive. That is, they change their shape with frequency of the wave generation. In this case, what we are trying to do is to have most of the energy of the wave around its center frequency or the main frequency. If we give just a simple sine wave, that won't be the case.
Same person says, why only tone burst excitation? Why no other form of excitation is used?
Okay, so as I said very briefly, a tone burst excitation helps with a drawback of the Lamb waves, which are dispersive. Dispersive meaning if you generate Lamb wave which has many frequencies, the wave at each frequency will travel with a different velocity. So after some time or after some distance, a sine wave that we have generated would look like a very different kind of wave. A tone burst excitation actually helps us maintain the shape, not 100%, but to a large extent. So the tone burst excitation actually helps us deal with the dispersive nature of the Lamb waves.
Okay, sir. How much would be the efficiency in aircraft structure?
I'm not sure what is meant by that, efficiency of aircraft structures.
We'll wait for him to clarify and go to the next question, sir.
Okay.
How does S3 receive radiation?
Okay, so the S3, which is the sensor 3 here, so we have this composite plate where we have attached one actuator, a PGT actuator, that we are actuating using a tone burst signal, which essentially is generating an elastic wave in the plate. So elastic wave meaning very small amount of, it's not exactly vibration, but it's actually a transient wave. Just imagine wave passing in a water when you throw a stone. So that wave actually would propagate to all sides, and in this case we are talking about S3, so which is on one side of it. So that wave passes through the structure. If we have delamination, it interacts with the delamination and comes to S3. Same way, of course, it comes to S7, S6, and S1, and all over the place. So it's essentially an elastic wave which is propagating through the structure, and we have sensors at those locations, again PGT sensors, which sense those waves. Any other questions, Sridhar?
I'm seeing, sir.
Okay.
Will you please explain what is the difference between diagnostic and prognostic?
Okay, so a diagnostic essentially refers to finding out if there is a damage in a structure. Of course, the diagnostics also refers to finding out, say, disease in people. So you see diagnostic centers which do blood tests and other things. So in a very similar way, diagnostics here refers to finding out if there is some kind of damage in a structure. Prognostics is predicting the remaining useful life. So how long would the structure be in operation before there's a catastrophic failure of the structure? So imagine a fatigue occurring on an airplane wing, and first we try to find whether there is a crack due to fatigue, how large is the crack, and the second stage would be, okay, if we leave this crack, if we don't do anything, and this airplane keeps on operating the way it normally does, after how many hours or months or years would this crack reach such a large size that the airplane wing would, say, break off? So these are the two aspects of diagnostics and prognostics.
That's all the questions, sir. And oh, there's one more. Why are we using 8 layers and not 9 or 10?
No, we can use 8 layers, 10 layers. We can also use uneven number of layers. Of course, when you have uneven number of layers, that laminate would not be balanced. Balanced in the sense, if you look at the thickness of the laminate or the number of plies above the midplane and below the midplane, they would be different. So unbalanced laminates have certain certain characteristics which are not very good. So generally we go for a balanced laminate, the equal number of plies above and below. So one can go for 8 layers, 10 layers, 12 layers. They are basically fine. We just go for 8 layers because that has significant number of layers, and we are not working too long to make that structure.
The question is the efficiency of smart structures in aircraft. Will it be compatible?
Will it be compared to?
Compatible.
Compatible. I'm not really sure what that person is referring to in terms of efficiency. If you know who that person is, you can tell him he is welcome to email me his questions in a little bit more detail, and I'll be glad to answer that.
Okay, sir. The question is, how do we inspect a bridge periodically in real life?
Okay, in real life, bridges, I know at least about the US, a couple of people, bridge inspectors, they would go to the bridge and inspect it visually. That's what they generally do. They usually don't use much equipment. Sometimes some equipments can be used. There are equipments that can be used, but the usual inspection is just very simple visual inspection. And of course, that has a lot of problems. It depends on the competence, the time that the inspector spends with the bridge. And if there are some problems which are hidden from view, they won't be able to find that out.
Sir, if there are no questions.
Okay.
Sir, there have been there is a request for your slides if you are willing to share them.
Yeah, sure.
You can email them to me. I will send it to that person, sir.
Okay. Yeah, I'll certainly email them to you. And do you know how many participants are there and where are they from?
Right now there are 52, sir.
Okay.
And I will have a list of their emails later after we close it,
okay.
if you need it.
Okay. Yeah, emails are. I would just like to know what country they are from. And,
sure, sir.
Yeah, something like that, just to get an idea about
sure,
where
sir.
this webinar is reaching.
Yes, sir.
Okay, Sridhar, thank you so much for helping me organize this.
Thank you for the webinar, sir, for so late at the time.
Okay. Okay, great. I'll send you my slides right now.
Thank you, sir.
Okay, thank you very much.
Thank you. Good night.
Thank you, everyone. Bye.
Bye.